Okay, here we go. So we are going to start with motion in AP Physics, and we're going to start specifically with motion in one dimension. And what I mean by that is you're either going side to side, so left to right, or you're going up and down. But when we're looking at one dimensional motion, we're not putting the two of them together. Now, if you look at these diagrams that I have here, right here, this is going to be one dimensional motion, and you're looking at cars moving. If you've ever taken any time lapse photography or nighttime photography, you have seen images like this, maybe, where you can get the lights, the lines that the lights make over time if you've kept your shutter open for quite a while. Now, these next two images, these are going to actually be examples of two-dimensional motion, but really I just wanted to give you some examples of what is motion. Okay, so we have a ballerina doing a leap. We have a basketball player shooting hoops. Okay, we've got bicyclists riding bikes, and there's a lot of different motion in this diagram right here in this picture. We have the rotational motion of the wheels. We have the linear motion of the bike. Okay, we have a runner, someone who is running on the roads. Okay, we have different types of motion. We have linear, rectilinear motion or linear motion, circular motion, rotational motion, like a ball, a soccer ball when you kick a soccer ball, or periodic motion. So the example there is like a grandfather's clock, but you could have any kind of pendulum would be periodic motion. Okay. Here we've got some more linear motion. So we've used cars, transportation, in two examples here. A hummingbird flying, now it's going to be in motion. A tennis player is going to move his or her racket, hit the ball. There's all different kinds of motion and forces involved in playing tennis. And then right here, I liked this diagram because this diagram is showing motion. It's called a motion graph. So I wonder if you can look at this and see, like, what can you tell me about the motion of the object? Do you notice the length of these arrows? The length of the arrows tells you something. What about the length of these arrows as opposed to the length of these arrows? If you have a shorter arrow, that's going to tell you that the velocity is going to be shorter or is going to be smaller. And here you've got an object that's moving a lot faster because the velocity is a lot longer. So also you have positive motion, and then it's almost like the object is standing still and then moving quickly in the backwards direction. Okay. It's almost like you're kind of walking to school and you go, oh no, I forgot something, after you've stopped to talk to someone for a second, and then you book it back home to go and grab whatever you forgot at home before you head back to school. So that's a really good example of a motion graph right there. So let's get started. What I would do if I were you is I would make sure that I have either printed the in-class practice problems or I've gotten them from class, or I would make sure that I had a spiral bound notebook that I'm taking notes in. Okay. So in this case, in this slide, we're talking about the difference between distance and displacement. So I just used the example of you are walking to school and then you realize you forgot something and you run all the way back home. Okay. The distance that you traveled, let's say you live half a mile away from school and you got all the way to school and then you go all the way back home. The distance you traveled is 1 full mile, but the displacement you've traveled is actually 0 once you're back at home. So your displacement is how far your position has changed. Okay, so distance and displacement, they're not the same thing. Distance is a scalar property where the direction does not matter. So you went 0.5 miles to school, 0.5 miles back. Your distance is 1 mile. Displacement is a vector quantity, and a vector quantity is something that's dependent on your magnitude and also your direction. So how high or low that value is, and then is it left or right, up or down? What's the direction? Is it an angle? And that's what's going to be important with two-dimensional motion. So displacement is a vector quantity of distance, basically. Displacement is the change in position specific to direction with some initial position, from some initial position to some final position. Okay. And then we use X in physics to represent our position. So you'll notice in your textbooks, you have XF minus X with a 0 or X naught. Okay. That means X in your initial position. You could have X2 minus X1, or you could have X final minus X initial. All of those are going to be different representations that you're going to end up seeing. So what that's going to look like for if you have X naught, it would be change in X equals X final minus X naught. Okay, or X at your 0 position. So left is typically negative X and right is typically positive X. I am one who switches my axes because I tend to lose my values of my negative values. I just make silly mistakes. So sometimes I'll flip my axes. And those of you guys who are in class, I will show you what I mean by that. But if you were to take like 2 rulers and you would make them perpendicular to each other, and you made up positive Y, and then to the right is positive X, and then you flipped that upside down, now you have upside down is positive Y and to the left is positive X. So you can do that too. But for right now, we're going to start with X is typically negative, or left is typically negative X and right is typically positive X. And also the units that you're going to be using here are meters for your displacement. Okay, so vector. And if you remember our little character over here, this is vector. And there's a really funny part in the movie where he goes, I'm vector. I have magnitude and direction. And I absolutely love that part in that movie. So vectors, again, are magnitude. Magnitude is the size of something, and direction is your alignment or your orientation. Are you moving north? Are you moving south, east, west, left, right, up, down? 30 degrees, 60 degrees, 45 degrees, what direction are you moving? So in AP Physics, you are expected to specify what the direction is with your final value. Now, a scalar property is a quantity that has no magnitude, or I'm sorry, has magnitude only and no direction. So scalar is a quantity that has magnitude only and no direction. So speed would be scalar versus velocity is going to be vector. Okay. So if you're running laps, if I do one full lap around the track, I was a runner in high school. And if I do one full track around the track, really, that's only my velocity is 0 because I have no displacement. I haven't changed my position. Whereas my speed, I mean, what's my speed going to be? Can I run a 400 meter in under a minute? And no, I was not able to do that. I could run a mile in sub 6. Okay, so we're looking at that's going to be my speed. How fast am I running a mile? Okay. Your distance versus displacement. So distance is your scalar and displacement is your vector. Okay. So a vector is a quantity has that both magnitude and direction. And in 2D motion, we're going to have to figure out what's our X value of my vector and what's the Y value of the vector. Okay. So in this case, I realized in this first practice problem, it says calculate a man's displacement for each of the following situations. But you know what? I used a girl for the first stick figure drawing that we have because it's very important that we recognize that I am female. And so ladies first. Okay. So if this lady goes from 10 meters to 40 meters, what is her displacement? So she goes from 10 meters to 40 meters. So in this one, our change in position is our final, which is 40 meters, final, minus our initial, which is 10 meters. And that's going to end up giving us 30 meters. And she moved 30 meters to the right or positive, or I'm showing that it's positive because I don't have a negative value there. So then we're always going to make sure that we include our units, and we want to make sure that we box our answers when we're doing these problems. Okay. For this class, when you're doing problems for homework, I am going to have you guys do notebook paper and pen or pencil. Take out your calculator and you're going to take a picture of your work. You have to remember, you guys, that this class is about you, and it's about your preparation for your next step, whatever that step is. So you're only cheating yourself if you're taking pictures of other people's work. I highly encourage you working together, but yes, you will be taking pictures with a camera and embedding it into your work for when you're turning it in. Okay. So right here now I have a man jumps in. And so this man, or this guy, this boy, ends up going from 30 meter, or sorry, from 10 meters. Here's my 10-meter mark. Okay. He goes from 10 meters and he's going to move all the way to negative 40 meters, negative 40 meters. So, and I'm seeing my negative 40 down here. So his displacement here is going to be negative 40 meters minus 10 meters. And that's going to be negative 50 meters. Okay. So you could give me that answer. You could also tell me that he has moved 50 meters to the left is another thing that you could do. Okay. Now, here's my guy, and my guy decides that he's going to run after this little lady over here and going to run this way to 10. Okay. And then run back to negative 20. Maybe saw some trash, needs to go pick that up. And then comes back over here to 30 meters. Okay. He's moving and grooving, and then decides that he needs to go back home. Okay. And so once he's come back home, here he is back at home. Okay. What is his displacement? His displacement in this case is going to be 0. His displacement is 0 because his initial or his final position is negative 40 minus negative 40. And then that's going to end up giving you 0. Okay. Now, in this case, if you wanted to figure out what his distance was, we have negative 40 to 10. So that's going to be 50. Okay. And then 10 to negative 20. So 50 plus 30 is going to be 80. Okay. And then plus another 50. So we have 80 plus 50 is 130 meters. And then going all the way back. So we've got 40, 70. So we're at 150 plus 70. So then that's 220 meters. Okay. I didn't write any of that down, so my numbers are off a little bit, but you understand what I'm saying. So the distance in this case is very different than displacement. Okay. Speed versus velocity. So speed is your scalar value, and your speed, your average speed, is your distance divided by time. Velocity is your vector. That your velocity is, by definition, your average velocity is the rate of change of position. So the rate at which your position is changing. Okay. So in this case, we have that our average velocity, V, is equal to change in position divided by change in time. Okay. Now, when you were younger and you were learning brand new math skills, like we're talking early algebra skills, you remember distance divided by time equals your rate. Okay. This is the same thing. Anything divided by time is a rate. Okay. But in this case, we're looking specifically at velocity. So velocity is change in position divided by time. Average velocity is positive when an object is moving to the right and negative when moving to the left. Now, like I said before, you can switch these, but you need to make sure that your direction is consistent throughout your entire problem. Okay. What is the average velocity when you travel in a circle? So if you think about it, when you travel all the way in a circle, and we just talked about this around running track. Okay. Here's my starting point. Here's my ending point. Guess what? Your average velocity is 0. That's not really fair. What a bummer. Anyway, your units are going to be meters per second there, okay? And you look at that in terms of, okay, displacement is measured in meters, time is measured in seconds, so we know that our units are meters per second. So always, always, always give me a numerical value, okay, and give me your units. Now, when you're looking at labs and data, significant figures matter, okay? Those of you who had me for chemistry, you know that when it comes to rounding, like I call things obnoxious answers. If you give me obnoxious answers, then I'm going to take points off, okay? So do pay attention to your significant figures. So if you look at question number 2 in your practice problems, we have a certain cheetah can run at a speed of 90 kilometers per hour. How much time is required for it to run 400 meters at this speed? Okay, so if we look at that, we know that average velocity is equal to change in position divided by time. And we are trying to solve for our time, okay? We're trying to solve for our time. So one thing that I have found very helpful in doing problems is the first thing that you do is you draw a picture, okay? You draw a picture, okay? And then you get your information. And you get that information from the question. So we have the speed of 90 kilometers per hour, and you're looking for how much time. So I like to box what I'm looking for because time is my question mark. And then we have 400 meters. And I'm going to write meters here just so I don't forget, even though it's right next to it, okay? And then the next one, so PIMA, E is going to be equation. So write your equation, which we already wrote our equation, and we want to manipulate that equation. So we are solving for time. So what I'm going to do is I'm going to multiply both sides by time. I get velocity times time equals change in position. Time, therefore, is equal to change in position divided by velocity, okay? The next thing is going to be your math, okay? So we're going to go E to M, PIMA. M is math, so do your math out. And then A is answer, okay? So that's the step that you should be following for every single one of these questions, okay? Sorry about my handwriting on this tablet, okay? That says answer right there. Okay. So if we look at this, we have position divided by velocity, but our problem is that we're in kilometers and we want to either convert our meters to kilometers or our kilometers to meters. So I'm actually going to convert our meters to kilometers. So I'm going to do that by figuring out, so that's my distance, my change in position is 400 meters. And if you remember from metrics, you're going to the left 3 times. So that's equal to 0.4 kilometers. Okay, so this is going to be 0.4 kilometers divided by 90 kilometers per hour. Okay. And so the reason I need to do that is because I need to make sure that my correct units cancel. So kilometers cancels. I have 1 divided by 1 divided by hours. So hours comes up and it gives me time in the end. So I end up getting 0.00044 hours. And if I multiply that by 3,600, that's how many seconds are in an hour. Okay, 1 hour is 3,600 seconds. So if you need to refresh yourself on dimensional analysis, please make sure that you do so, Okay, there are tons of tutorials that you can find online or you can ask during class or tutorial, and that's going to end up giving you that your time is 15.98 seconds, okay, or about 16 seconds, okay. 16 seconds is still not the right number of significant figures, but I would prefer 16 seconds in this case, okay. And then I'm going to go ahead and box my answer or circle my answer. Okay. So some people would ask, well, do I have to answer in seconds? Okay. The answer is no. I mean, you could answer in hours. If the question doesn't state specifically, College Board is not going to take off points. Okay. Also, when it comes to significant figures, a problem like this, if you answered to and you said 20 seconds because you know significant figures here is 1, and they know from giving you that question, they look at the question and go, oh my gosh, we only gave them 1 significant figure, they would take 20, okay? They do want a more exact answer, but you don't want it, you do want to round at some point. So just make sure that your answer is reasonable for the type of problem that you're doing. Okay, so instantaneous velocity. Now, when you're driving, a lot of you guys already have your license. Not all of you do. Okay, when you're driving, you have what's called your average velocity. Your average velocity is at an infinitesimally short time interval. So that is your velocity at an instant. So I look at that. Your instantaneous velocity and your instantaneous speed are going to be the same. So this is going to be like you're reading on a speedometer. Okay, so you're going to see terms like instantaneous velocity, and that's how fast you're going at an instant. Okay, so in this case, we have chasing trains. So we have good old Thomas and Percy. My kids were not big Thomas and Percy kids, but you know, some people are. Okay, and so you have our 2 trains, train A and train B. And it says both traveling to the east on parallel tracks, where train A is initially 20 kilometers behind train B. If train A is moving at 60 kilometers per hour and train B is moving at 50 kilometers per hour, how long will it take for train A to catch up? So if you look at this, okay, you have train A, okay, train A is initially 20 kilometers behind, okay. So train A and then train B. Okay, and this is 20 kilometers. Okay, and you're trying to figure out at what point will train A go the same distance, so that, not the same distance, but going to go meet up with train B. So we have position X here, okay? So if you look at it this way, A, okay, position for A is going to be equal to 20 kilometers plus XB. And then XB is going to be equal to XB, okay? Now it says, how long will it take for train A to catch up, okay? So when you're looking at that, you know that train A and train B have the same amount of time. Train A time is equal to train B time, okay? So the first thing that you can do is you can, what I would do is I would do that I know velocity is equal to change in position over time, okay? And so from here, I know that time is equal to change in position divided by velocity. So therefore, if both times are equal to each other, then I know that 20 plus x divided by my velocity of A, which is going to be 60 kilometers per hour. I'm not going to include my units for right now, okay? And then right there, I'm going to have that that's equal to x divided by our 50 kilometers per hour, okay? And then the kilometers per hour is actually going to end up canceling, okay? And so we end up getting 60x is equal to 2 times 5 is 10, add our 2 zeros, plus 50x, okay? So then I know that 10x is equal to 1,000, okay? So I know that the distance that's been traveled, the distance for B that's been traveled is 100 kilometers, okay? That's the distance that B has traveled. So now, because I know time is equal to displacement divided by velocity, I'm just going to go ahead and plug that in. For B, I have 100 kilometers divided by 50 kilometers per hour. Kilometers is going to cancel. Hours is going to kick up to the top. So you end up getting that our time is 2 hours. Okay. Now, there are some of you, because I know some of you, that are looking at this and going, there's a different way to solve this, and it's an easier way to solve it, and it makes more sense. That is fine. If you are showing your work and you are using physics and physics principles and physics equations, that is fine, okay? You can use more than one equation, more than one way to solve a problem. When I was in high school, my AP calculus teacher used to run around her classroom, and her name was Mrs. Foff, and she used to say that her name had 3 F's for every A, and that's why she was named Mrs. Foff. She was a pretty harsh and strict teacher, but she used to always say, there's always more than one way to skin a cat. There's always more than one way to skin a cat, which is such a weird phrase. But every single time I think about everyone's got their different ways of doing things, I think, okay, there's more than one way to skin a cat. So go ahead and watch this video. So right now, what we're going to do is you are going to be thinking throughout this week, how would you determine where these two cars will crash if they are placed 6.5 meters away from each other, but facing each other? What can you measure? Okay, well, we could measure the circumference of the wheels. We could measure the size of the cars. We could measure, maybe you're thinking, how fast? Okay, how would you measure this? What data would you collect? So if you watch this.
So right here we have 2 different velocity carts, and students who are in class this week are going to be using these carts to measure something about them. So if I wanted to compare these 2 carts, okay, and I've given you actually, I've given you our problem. Our problem is, how would you figure out where a bullseye needs to be placed in order to have these cars run into each other? So how would you determine where these cars were going to run into each other if they were 6.5 meters apart? So what you're going to do this week is you're going to come up with the calculations and figure out where exactly 2 carts are going to end up crashing into each other. And then next Monday, I am going to run the test on the carts that you've told me are going to run into each other and where they're going to run into each other. So let's see, what can we measure about these carts? Could we measure how long they are? Could we measure how tall they are? Okay, do they look very different? And when we're comparing and contrasting them, what about if we measured the diameter or the radius of the wheels? We could measure those things. Those are values that you could measure. But are those values going to be valuable in helping us figure out where those cars are going to end up crossing? Okay, and so that's kind of your question. And if you're asking yourself, like, what's the most important question that should be on your mind? The most important question to be on your mind is, how fast are they going? Okay, so if I turn on this car, okay, and I turn on this car, okay, the wheels are going to be moving differently. If I start them at the same exact point, what do you observe about them? Ready? Go. Okay. What observations can you make about those cards?
Okay, so when you're making those observations, another thing I want you to think about, something I want you to think about every single time that you are given a problem that you are being asked to do a lab for, you want to ask yourself, what data can I collect that I can graph to come up with an answer? What data can I collect that I can graph, and how can I graph it to come up with an answer? And then once I collect that data, what will the graph look like? And then what will I do with that graph? What information can I pull from that graph? So I want you to think, what can you measure here? Okay, make sure that you're using correct physics units. What can I measure here in order to collect the data, to graph the data, to figure out some variable, some value that's going to help you determine at what point these cars are going to end up crashing into each other. So speaking of graphing data, you need to know how to graph. And I believe that all of you know how to graph, but I really just want to double check and make sure that you know how to create a reliable graph in AP Physics. So in order to create a reliable graph, I kind of use this phrase. I heard this from a local teacher. Every graph talks. Every graph has a title. So you do, in this case, you would do position versus time. You would do Y versus X. So you are going to do your dependent versus your independent variable. Okay. A is going to be your axis, where your axis, like where your distance goes and where your time goes. You have labels. So you have labeled your axis with your units, and you've also labeled it with the name. Okay. And then your K is going to end up being your key. Okay. So if you have more than one graph, you want to include a key of what does the data tell you? What are the lines? What are the, if you have multicolored plot points, what do those, is that run 1, run 2? What does that represent? Okay. And then your S is going to be your scale. Okay. And then, so what you also need to do, so you need to know what the right data is to be plotted. And instead of connecting lines, so some people will like play it like connect the dots, okay? You're not going to connect the lines. You're not going to connect the dots. You're going to find the best fit line. So the best fit line is going to include the average line through the data. Now, in this graph right here, you can see that that best fit line goes through 0. Your best fit line should not be forced through 0. Why would your best fit line not go through 0 even if you expected it to be at 0? What would cause that difference? Okay, if you think about it, then what would actually cause that difference is error. How much error is in the lab. So you would use that information in your error analysis. So one thing I want to do after talking about what you're going to graph or how you're going to graph, I want to talk about what do the values mean? Because I think that this is really important. As you've moved through life, you have learned how to find the slope of the line. That's something you can analyze about this graph. So if I find the slope line, everyone's going to say, I have my Y, my rise over my run, right? Okay. Everyone says rise over run. That's your slope. Slope equals we call that M, which is change in Y over change in X in math, right? Okay. But even though we're doing mathematical stuff, okay, we're not in math. And so what is our value for Y? So our slope is going to be change in position. So our slope in this case is going to be equal to change in position, change in X, divided by change in time. Well, did we just talk about what that is? We just talked about what that is. Change in X divided by change in time. Oh my gosh, that's your velocity. Your slope is always going to mean something. If you have a linearized slope, it tells you something. It's usually a value. The slope of that line is a representation of a value. And in this case, it's velocity. So, oh my goodness. Well, if we look at this, we have y for our equation, y equals mx plus b. But let's use substitution, like for the values that we're using scientifically. What's our y value? Our y value is our position. So we have y is position is equal to m, which is our slope, which is our velocity. X is our time, plus b. What's b? B is going to be our y-intercept, which is our initial velocity. So what you see here, okay, this right here, okay, I'm going to write it back up here, x equals vt, and this is a constant velocity, your constant slope, plus x initial, or velocity is change in x over time, or x final minus x initial divided by time. So just by analyzing this data, you have now determined one of the kinematics equations, one of the kinematic equations. And this is huge, okay? Now, looking at this graph, another thing, I don't know if you know how to look at the data that's given to you from a computerized program. So looking at this graph right here, your slope is 25.025. Since your slope is 25.025, what that's telling you is the velocity of this object is 25.025 or 25 centimeters per second. Now, I prefer for you not to use centimeters. Please do not use centimeters. Please convert to meters, okay? I want you to figure it out in meters per time. But that's how we use the information in a graph. Now, what if I have a velocity versus time graph? Okay, again, the slope of a linear data set always is going to tell us something important. We see a consistent slope here. What does that mean? That means for every, 0.05 seconds, this object is going to change its velocity by a certain value. Okay, and in this case, it's going to change by a value of 9.8. Okay, so for every 1 second, it's going to change by 9.8. For every 1 second, it's going to change by 9.8. Okay, so looking at this, what does that mean? Well, our slope in this case is change in velocity over time. If you're changing your velocity in your car, how do you change your velocity in your car? You're going to go from 0 to, say, 25 miles per hour. What are you going to do? You're going to push on the gas. The gas pedal is also called the accelerator. So the slope of a velocity versus time graph is equal to your acceleration. And we can do the same thing that we just did. We have acceleration times time. Okay, acceleration times time. If we're looking at y equals mx plus b, I'm going to write it up here. Y equals mx plus b. Our y value is our v, or v final, is equal to acceleration times time plus our v initial. If our v initial is 0, fine. You don't have to include it, but we still include it in our equation. So that right there is another kinematic equation. Okay, or acceleration. So what is acceleration? Acceleration is going to be the rate of change of velocity. The rate of change of velocity. So v final minus v initial divided by change in time, divided by the time that it takes. It is a vector quantity. Magnitude and direction matters. The units are meters per second squared. Okay, so what is deceleration? When we talk about deceleration, we're talking about how an object is slowing down. Whenever the magnitude of velocity is decreasing, so say you're going from 8 miles per hour to 4 miles per hour, which is crazy. Let's talk like real car. Let's say you're driving down the road and you see a police officer and you put your foot on the brake, okay? The brake is going to apply a force against the wheels, cause you to slow down. So you're going from, say you're going 45, or say you're going 50 in a 45, and you hit your brakes. And so now you're going 50 and you go back to 45 or 40. Okay. That's going to be deceleration. My velocity is decreasing. Okay. It does not have to be negative though. And that's what we're going to look at next. So a certain bicycle is initially moving at 5 kilometers per hour when it begins slowing over the course of 25 seconds. What is the magnitude of the bicycle's acceleration during the stopping process? So we have 5 kilometers per hour, okay? And we're going to end up converting that to meters per second, okay? So for every 1,000 meters, I have 1 kilometer, or for every 1 kilometer, I have 1,000 meters. Kilometers cancel. Then I'm going to convert my hours. For every 1 hour, I have 3,600 seconds. This is 1, okay? So now my hours cancel. They're on opposite sides of the dividing line. This ends up giving me 1.39 meters per second. So my acceleration is equal to change in velocity over time. Well, let's go back and look at our information. We have 5 kilometers per hour, okay? And it says 25 seconds, that's my time. What is the magnitude of the acceleration? So I'm solving for acceleration. Acceleration is change in velocity. So it's initially at 5 kilometers per hour. It begins to slow over the course of 25 seconds, okay? And so in this case, it begins to slow until it's going to stop. So during its stopping process. So your final velocity is 0 minus 1.39 meters per second divided by our 25 seconds. And that's going to end up giving you a negative 0.056 meters per second squared. However, the question is just asking for magnitude, so you don't have to have that negative in there. Like you wouldn't get marked down if I'm just asking for the magnitude, okay? So let's look at our next question. A car is moving in the negative direction at a velocity of negative 9 meters per second. So negative 9 meters per second. And then it then undergoes a positive acceleration of 0.4 meters per second squared for 10 seconds. What is the car's velocity at the end? So we're looking for V final. We know acceleration, okay, so you could draw a picture here. I'm not going to for the sake of time, but I'm looking at my V final minus V initial divided by time, okay? So my acceleration times time plus V initial equals V final if I manipulate this whole entire equation, okay? You might want to pause, stop, make sure that you know how to manipulate that equation, okay? And so what that ends up giving me is I have positive 0.4 meters per second squared times 10 seconds plus my initial velocity is negative 9 meters per second. Notice seconds squared and seconds cancel. So now I'm adding two like values, okay? And I end up getting a value of negative 5 meters per second. So I'm still going in the negative direction, but I'm going slower in the negative direction, okay? So directions and sign. Why do we know? Why does it matter? It matters because if you start throwing around the wrong signs, then you get the wrong values. And this is by far and away the most frustrating part of one-dimensional motion, okay? Those of you guys who are wondering, this is the same as chapter 2 in your Guy and Coley textbook, which is also your Paul Hewitt chapter 4, okay? Paul Hewitt is conceptual, so there's not going to be as big of a focus on the numbers. The conceptual and understanding the concepts is extremely important, especially in AP Physics, AP Physics 1. But the numerical stuff, the reason I really push the numerical stuff also is because when you move on to college, whatever that next step is for you, you're going to have to do the numerical stuff. And that's the stuff that starts to trip you up as you get older, okay? So the rules for 1D motion, it is standard to label quantities as positive if right or up and as negative if left or down. The direction of velocity indicates the direction of motion at some instant. The direction of acceleration indicates the direction of the change in motion. And you'll realize in the next full unit that we do, your acceleration is in the direction of a force that's acting against you to slow you down, or to change your velocity, How about that? Okay. So if something is speeding up, velocity and acceleration are in the same direction. If something is slowing down, velocity and acceleration are in opposite directions. So I really like this graph because I think about if you take a baseball and you throw it up in the air and then you catch it, it is slowing down until it comes to a stop. So at this point, it's slowing down, meaning the slope of that line is actually getting less steep. And then it's speeding up, coming back down to you. Okay, it's speeding up, coming back down to you. And then all of a sudden, your slope is getting bigger. So then here you're speeding up and almost stopping, okay? So we're going to be looking at graphs a little bit later as well, not today, but on another day this week. So the very last question that we have for today that we're going to look at is, what are the directions of velocity and acceleration for the following objects? Assume standard positive, negative directions for left and right. So object is moving to the right. So if it's moving to the right, velocity is positive. If it's slowing down means acceleration is opposite. So therefore, acceleration is negative. An object is speeding up while moving to the left. Moving to the left, velocity is negative, okay? And then it's speeding up. Speeding up, acceleration is the same. Same sign. So acceleration is negative as well, okay? So it's kind of a brain twister, okay? But it is important for you to understand the directions and the values of the signs. So if you have any questions throughout this time, please go ahead and reach out to me and I will be happy to help. Sorry that was such a long video, but hopefully it was very helpful as you move on to start your homework.